Good morning. Today we will look at the equations and filtering compressing. Excuse me. We'll look at equations governing the rectifier circuits as well as the addition of a filtering capacitor. Okay, and then a little bit of time at the end, we'll introduce Zener diodes. Okay. So we looked at half wave, full wave rectifiers, center tap full wave, and bridge rectifiers, right? So in a half wave rectifier, we saw that a single diode is used to convert a alternating waveform into a pseudo DC waveform, where the diode conducts in one half cycle, and is off for the other half cycle, thus giving us a pseudo DC waveform. At least that's what I like to call it. This is also referred to as a pulsating DC, depending on who you talk to. Our book uses pulsating DC. I don't have any problem with the term. I like to call it as AC/DC. It's both AC as well as DC. So AC/DC. Now, the question is, if it is still it's still varying its value with respect to time, how can you call it as AC? And the answer is yes. It's not a true DC waveform, right? It's not a true DC waveform. It is not going negative, only has a positive value. And so to smooth out those peaks at the output, we add a capacitor. And because it is filtering out the AC waveform, we refer to it as a filtering capacitor. Okay, it's a filter capacitor. So first, I'd like to point out that in an ideal diode analysis or an ideal diode model, the diode doesn't require any extra voltage to turn on. But in a real life diode or a real life circuit, we would be better off using a constant voltage drop model, because a certain amount of the voltage from the input is required to turn the diode on. Okay, so the output voltage will be reduced by the diode turn on voltage. Right? In the constant voltage drop model, be about 0.6 volts. Which of course V on will change depending on which diode you're using. Right? Germanium diodes are about 0.2 to 0.3 volts. Silicon diodes are 0.6 to 0.7 volts. If you use an LEDs, it'd be more than 1 volt, 1.2, 1.3 volts. So that is one thing. Next, we talk about the filter capacitor. Okay, so here's a rectifier circuit or a half-wave rectifier circuit with a filter capacitor attached at the output. Now, before we get into that, I'd just like to recap a little bit of the sine wave representation, mathematical representation of sine wave. So I'll take you back to circuits. Circuits 2, I believe. We have a time varying signal which looks like this. Right? In the time domain, you have a sine wave. If we take this as 0, meaning the beginning of our analysis, we can represent it as a vector rotating in the complex plane, rotating counterclockwise. Right? This is the peak value. That is also the length of that vector. It rotates with a speed of omega, 0 and 360 degrees. 360 degrees is here, which is also 2 pi radians. Here's pi, or 180 degrees, pi by 2, and 3 pi by 2. Look familiar? hopefully, circuits. So we represent, the mathematical representation of the sine wave is V of t. Voltage is fluctuating as a function of time. It has a different value at any given point in time, and that is represented as V peak sine omega t plus or minus theta. We keep omega, the angular frequency, in radians per second, theta in degrees. We want to keep it separate because we want to represent the time varying waveform as a vector. Phasors, remember phasors? We want to represent it as a phasor in the frequency domain. And so phasor for this can be given by Vp with an angle of theta. Okay. Now, when we have our input waveform or half wave, or draw this down right here. Okay. And then right here. Okay. So this is a half wave rectified waveform, right? Select two peaks. One time period, of course, extends from here to here. And that is noted by T, lowercase t, capital T. Omega is 2 pi f, and f is the inverse of the time period t. Okay. So for a half wave rectifier, we have one positive peak, or depending on where we connect our diode, we have one negative peak. So you have one peak for every time period, right? So the time period still remains the same. If you apply 60 hertz, your output still has 60 hertz. Okay. All right. So now, as I was stating earlier, this is neither full DC nor is it full AC, right? Pseudo DC or pulsating DC, if you will. Now we will use the energy storage capabilities of the capacitor, more specifically the energy transfer phase of the capacitor, to remove this AC component and make it as flat as possible. So in an ideal circuit, let's say you have an ideal diode here, you have an ideal capacitor here, okay? In the positive half cycle, this is how the circuit will look like. So positive half cycle, the voltage source can be represented as a battery that has polarity with plus up top, minus at the bottom. Diode can be represented as a resistor in forward bias. That resistor signifies the diode forward resistance. Okay. If you recall from lab last week where you calculated the diode resistance in forward bias, that's what this is. So we can call it RF, diode forward resistance RF. Capacitor C, diode is forward bias, current starts flowing through the circuit. Capacitor charges to the peak value, right? Peak value. And this would be VC. VC. Yes. Good point. That's actually my next point. So RF is small enough so that tau, the time constant of the circuit, is also small. Thus, Vc reaches V out, and V out in this case, if it's ideal, then it's simply V peak. But since we spoke about the diode voltage drop, it will be Vp minus the turn on voltage V on, one single diode voltage drop. Okay. So capacitor reaches a charge of Vp minus V on. All right, 10-second pause. Let me know if you have any questions. So far, so good. Okay. So in the positive half cycle, capacitor charges through the diode. And if you look at our waveform, this is T, this is V out or VDC. We are assuming that the time constant is small enough that the capacitor reaches full charge. Okay. But at the same time, during the discharge portion, we want the time constant to be large enough that it doesn't discharge very quickly. Okay. So the capacitor charges, reaches full charge at the top of the peak. Now, in the negative half cycle, let's draw it on this side. Negative half cycle. Polarity is reversed, so we can write that, or sorry, we can draw that as a battery with negative up top and positive at the bottom. Diode is now reverse bias. It behaves like an open circuit. Real life diode, we can still model it as a resistance of very high magnitude, almost infinite. Okay, because the diode is reverse bias. It's open, it's very, very large. Capacitor, which was charged, now begins its discharge. And this is reverse resistance. And it's a very large value. So the time constant tau for discharge is now RR times C, which is again a large value. So the capacitor begins discharging at a slow rate. And eventually, at some time in the future, Vc would reach 0 volts. But before it can reach 0 volts, its discharging is interrupted and it begins charging again. Okay. So the first positive peak hits, capacitor starts charging. When the negative half cycle arrives, the capacitor begins discharging. Diode is behaving like an open circuit. Capacitor starts discharging, and we design our circuit such that the time constant is large enough that the capacitor discharges at a very slow rate. What is shown in the waveform on the left, right here at the top, is an ideal capacitor, an ideal diode. So an ideal diode behaves like an open circuit. Ideal capacitor will hold its charge indefinitely. And so V out across the capacitor is simply a flat line. So again, this is an ideal circuit up on the left. Ideal diode with ideal capacitor. Okay, so it doesn't discharge at all. At the output, capacitor just displays its energy. Okay. All right, 10-second pause. Write it down, think over it. Let me know if you have any questions. Yes. So the question being asked is, what if the capacitor doesn't charge up in the first half cycle? Well, there is a fine line, and there's a very good point. There's a fine line between keeping the time constant small enough that the capacitor reaches full charge, but then it must be large enough when it's discharging, so it doesn't discharge all the way to zero. So you, as a design engineer, would have to figure out where that line is. Now, obviously, this is just one small portion of a power supply. Now, power supplies have multiple different components to obtain a flat line, namely the next topic, which is basically Zener diode regulation, which gives us a very flat line. But the point still stands that we want it to be somewhere. So there are design trade-offs. We want it to be somewhere in the middle, where it's small enough that it reaches full charge, but then it's large enough that it doesn't discharge completely to zero. And that is easily possible because in the reverse bias, the diode resistance is much, much larger than it is in forward bias. But in a practical circuit, it is not going to discharge to the diode. It is going to discharge through the load resistance. There will be a load resistance to the right of that capacitor, right? Or the load circuit, whatever that load circuit is. So the capacitor is now supplying energy to that load. So depending on what the load resistor is, that's where we will, that's how the tau time constant will be controlled. And that actually is coming up in just a few more points when we look at the equations. But for now, does the explanation make sense? In the positive half cycle, capacitor charges, negative half cycle, it's disconnected, so it begins a discharge. And because it's discharging, it is supplying energy to the output. It is effectively removing the AC behavior of that waveform. Previously, without the capacitor, if we were to measure the DC value of that waveform, it'd be like taking the area under the curve, which would be only these two peaks for the two time periods, right? Or if you're just considering one time period, it's just one half peak, area under the curve. Think of it as mountains of dirt, and you flatten it out, and that level will be somewhere over here. It'll be 0.38 times VP, approximately. Okay. But now, in the empty spot, which is right here, the area under the curve has now gotten larger because the capacitor is supplying its stored energy. Okay. That energy is coming from the capacitor. It is not coming from the input signal. The input signal has turned the diode off, so it's not reaching the output. That energy right here is coming from the stored energy of the capacitor. Okay, because the capacitor is where we are taking the output. Does that make sense to everyone? Okay, it's a discharging portion of the capacitor, so the capacitor is supplying its stored energy to the output. And so now your DC level has risen up. And because the DC level has risen up, we can now consider this waveform as an actual DC waveform. However, because it's not an ideal capacitor, actually, it still leaves behind an AC component. Okay, it's almost a flat line, but it's like the surface of the ocean. If you look at the surface of the ocean from very far off, it looks almost flat. If you look at it closely, you'll see ripples of waves on the surface of the ocean. And hence, this last remaining vestige of the AC waveform is known as the AC ripple. Okay. In real life supplies, capacitor values around 1,000 or 10,000 microfarads. And for a 10 or 12 volt DC supply, the ripple voltage is probably 0.1 or less. Yes. Not a diode, but we would, so the point being made is, or the question being asked is, can we add another diode or a capacitor to make it even smaller? The answer is yes. We can add another capacitor, but it'll be the same thing as increasing the value of the capacitor. So it'll be very, very small. And students who did the lab yesterday, we used the electrolytic capacitor. You saw how small the ripple was when you used the electrolytic capacitor. If you have the lab tomorrow, then we can test it out. We can test it out right there. We have two capacitors in our lab kits. Smaller capacitor, you'll still have a larger ripple voltage, but a bigger capacitor, the ripple voltage is in millivolts. Very, very small. Okay. And this is jumping a little bit ahead, but in a true power supply, one of the minimum things we would add at the output would be, after the capacitor, we'll feed this into a regulator. The simplest of regulators is a Zener diode. So we would connect a Zener diode after the capacitor or in parallel with the capacitor. The Zener diode holds its output voltage constant for any level of input. Once it turns on, that ripple will also go away. So we obtain a near flat DC line using multiple different components. But as of now, we are just looking at the diode and the capacitor. Okay. So that's the AC ripple. Okay. And it is noted as a VR, ripple voltage VR. It is measured in both peak to peak as well as in RMS. Okay. And because it's AC, so it has a top and a bottom. And so we refer to it as a peak to peak AC ripple voltage. Now, look at the x-axis. Okay. The diode should turn on when V in goes positive, right? V in goes positive. But at this point right here, where the diode is supposed to turn on, the capacitor is holding the cathode of the diode at a higher voltage level. Okay. This is the voltage level right there. It's not quite zero, right? It's way above zero. So the cathode of the diode from this circuit, right? If it goes, in the negative half cycle, capacitor is fully charged, it's discharging slowly, but it is still positive at this end, which is where the cathode is connected. So when it comes back to the positive half cycle, this end, the cathode, is held at a higher voltage because of the capacitor. So the diode doesn't even turn on when V in goes positive. This is the point where V in goes positive. This is the point where the diode is supposed to turn on. Right there. Right? When V in goes positive. But because the capacitor is holding the cathode at a positive level, the diode is reverse biased, and it will not turn on until V in reaches this point. Right there. So V in must be higher than the capacitor voltage for the diode to turn on. So that is another consideration in the design process. And then once it turns on, it stays on for this portion. And this is known as delta T. So the diode is only conducting for a little portion of the input cycle. And that is signified or noted as delta T. And that is known as the conduction time. So I'm going to write it down right here. This would be in seconds. And then the angular representation of delta T is theta C and is known as the conduction angle. Conduction angle. Okay. The ripple voltage can be given in terms of the voltage, time constant, and the time period. So VR is the input voltage minus the diode turn-on voltage, Vp minus V on, times one time period T times the time constant RC. Okay, RC. So delta T is the conduction time. That's the time that the diode is actually on. For the rest of the time, it's off. And then angular representation of conduction time is theta C, conduction angle. Ripple voltage can be described in terms of the input voltage. So Vp minus V on times the time period divided by the time constant RC. All of the values are known. That begs the question, what is this R? And that brings me to that earlier point of the question that was asked, that R is basically the load. And so as an engineer, you would be designing a supply to work with a specific load, or if you're designing a generic power supply, you'd be designing it to work with a wide range of loads. Okay. Typical power supplies, for instance, back in the day, we used cordless phones. You all remember those? Perhaps you used it when you were younger, maybe. No? All of those cordless phones used to come with a small adapter, and you plug those into the wall. So those were, of course, designed to work with only one specific device, one specific cordless phone, right? If you try to use it with something else, it may not work, or it may not work as well. Now everything is standard spec USB. And so USB spec is standard 5 volts. You can change the current. The minimum spec for 5 volts is 500 milliamps based on all the computers that we have. Chargers now come with varying voltages and with varying currents, but you can still obtain the standard spec from the output, from your chargers. Okay, so those power supplies are designed to work with a wide variety of loads. Okay, so as a design engineer, the value of that R is a consideration in the design process. Whether you are designing it to work with one single device, or whether you're designing it to work with a wide range of devices. Okay, in our case, right here, we'll simply say it's a single value, and we will choose it so that the time constant is sufficient enough to give us a near flat DC line. All right, 10-second pause. Let me know if you have any questions. So far, so good. Okay, so from ripple voltage, we can go to current. Simply rearrange the terms, and we can write ripple voltage is Vp minus V on divided by R times T over C. And we can take this term and define it as IDC, the DC current, Vp minus V on divided by the load resistor. Simple Ohm's law. Output voltage divided by the load resistance. The conduction angle, theta C, delta T is theta C over omega. And theta C can be written as the square root of 2VR over Vp. VR over Vp. There's one more term, and that is the peak inverse voltage or the peak reverse voltage. This is the voltage that a diode must be able to handle in reverse bias without breaking down or without entering the breakdown region. And for a half-wave rectifier, that needs to be approximately equal to 2 Vp. Okay, at least twice as much as the peak value. With the silicon diodes that we use, it's not much of a problem. The 1N4000 series can go all the way from 50 volts at the lowest level to 1000 volts at the highest level. So from 1N4001 all the way up to 1N4007, it can handle all the normal voltage ranges. All right, questions? No questions? Okay. All right, then let's look at equations for the bridge rectifier. So the explanation that we used, that we just presented right here for the half-wave rectifier applies equally to full wave, the center tap full wave, and the bridge rectifier, except the frequency is now doubled. Because every half cycle is now rectified in the positive direction, the capacitor charges and discharges twice as much as for a half-wave rectifier. Okay, so the frequency is twice as much. The waveform looks very similar. The equations are also very similar, except for a few changes. Because there are two diodes in a bridge rectifier circuit for every half cycle, the turn on voltage is now twice as much, right? So 0.6 times 2. That requires 1.2 volts of the input signal for the diodes to actually even turn on. If the input is less than the diode turn on voltage, it's not going to turn on. And so the output voltage for a bridge rectifier can be written as V out or VDC as the peak value minus 2 times V on. Okay, 2 times V on. Equation for IDC, the current is the same. We can write it as Vp minus 2V on divided by R. And then ripple voltage, very similar expression, except now because the frequency is doubled, everything is doubled, so we add a 2 in the equation. So it's Vp minus 2V on divided by R times the time period divided by 2C. Simply IDC times T divided by 2C. Delta T is still the same. It's theta C over omega. And theta C is square root of 2VR over VP. The only difference is that because there are two diodes in series, you can use a lower level diode, meaning the peak reverse voltage is only VP, not twice as much as VP. Because each reverse voltage is now divided between two diodes in series. Okay, between two diodes in series. Now, add questions? Yes. No, so this is simply the ripple voltage IDC times T over 2 times C. It's because the frequency is double for every single time period. If we apply 60 hertz wave, now we obtain a waveform which is 120 hertz, twice as much. So the equation, I mean, there's a small derivation in there in the equation, but it turns out that it's twice as much. So it's T, for a half wave rectifier, it was T over C. For a full wave, it's T over 2C. Here? No. So this R was here. We simply rearranged the terms. So here. Right? It was time period divided by time constant RC. And so then we rearranged the terms. We took the R inside here to describe it as the current going to the circuit. So it's the exact same expression, except for a full wave rectifier, it's 2C and 2 times V on. That's the only difference. So the R is still there. It's still the time constant. Yeah, any other questions? Center tap is also almost the same, except that the peak inverse voltage must still be twice because there's only one diode for each half cycle. So for a center tap, V out or VDC is equal to VP minus V on, same as the half wave because there's only one diode. And then VR, the ripple voltage, would be the same as the bridge rectifier diode because there's only one diode in each direction. So VP minus V on divided by R times T over 2C. Full wave rectification. Delta T is still the same. C over omega. And theta C is 2VR over 2VP. And peak inverse voltage or peak reverse voltage is 2 times VP. For all three of them, you can see there is a direct relationship between the ripple voltage and the capacitor value. Okay. The VR equation for all of them includes the load resistance as well as the capacitor value. So if we are designing this circuit, if you're designing a power supply, we wish to know what the capacitor value should be. Well, then it comes from our desired application. How much ripple voltage do we want, or how much AC do we want to eliminate, right? Typically, as I said, if you use 1,000 microfarad capacitor, your ripple voltage would be less than, like 100 millivolts. Probably not even that much. Probably in tens of millivolts. Okay. So next slide is a comparison all the equations for all three rectifiers. Okay. Same equations, we are simply rearranging the terms for the capacitor. So based on the desired ripple voltage, we can choose a capacitor that is large enough to give us a almost flat DC line. Okay. It's simply a summary of the previous equations. All right. Good? Okay. Any questions come to mind? All right. So real life supplies, as I stated, this is simply the first few steps. There are a lot of other components that go into making a reliable DC supply. One of the easiest things we can do to obtain a near flat DC line is basically add a Zener diode at the end, meaning after the capacitor is done its filtering, we add a Zener diode in parallel with the capacitor to hold the output voltage constant. So the next topic which we are introducing is the Zener diode. Now, if you think back to the beginning of the chapter, we spoke about PN junctions and PN junctions in reverse bias specifically. In reverse bias, with increasing voltage, with increasing electric field, the depletion region keeps getting wider and wider until the diode reaches a region known as breakdown, where a whole bunch of carriers acquire enough energy to cross over the junction and current flows in the opposite direction. Okay. The breakdown in reverse bias occurs due to two different effects. One effect is the Zener effect, which is at the lower voltages, and the other effect is the avalanche effect. Okay, but in general, and this was stated earlier, I'm stating it again, in general, it has come to be accepted that no matter what the effect is for the breakdown, it is all referred to as Zener. Okay, so Zener diodes are specifically manufactured or fabricated with heavy doping in a small region. So a huge amount of dopants in a very small region to create that Zener effect at all voltage ranges. So you can buy Zener diodes ranging from like 2 or 3 volts going all the way up to hundreds of volts. Okay. The example circuit shown here uses a Zener diode of 5 volts. It is also similar to what you're using in the lab. I think the lab Zener diode is about 6 volts or something. Okay. But Zener diodes are used exclusively in the breakdown region because they are fabricated exclusively to work in the breakdown region. So Zener diodes are always reverse bias. And hence you see in the circuit, the cathode is connected to the positive end of the power supply. Okay, so Zener diodes are used exclusively in the reverse breakdown region. It holds the output voltage at a near constant level. In the forward bias region, they work as normal diodes. In the reverse bias, they hold the output voltage near constant. So there could be huge amounts of current flowing through the Zener diode, but the output voltage will remain a near constant. And I'm going to draw out the characteristic of the Zener diode in reverse bias. And this is going to be a bit exaggerated. We have minus VD minus ID. And let's see. This is very exaggerated or highly exaggerated. If you recall lab 2, where we did the SPICE simulation, in reverse bias, we had to zoom in into the picoamp range to even see a value or a characteristic like this. Okay, so this is typically in the nanoamps or picoamps range. Last week, when we did the reverse bias diode characteristic using sweep and go, we asked you to zoom into the y-axis, and we were able to see this characteristic right there. Okay, the diode characteristic passes through the origin. So in the forward bias and the reverse bias, in the reverse bias specifically, you have this current that's flowing, which is of course the reverse saturation current. In real life, again, it's in the nanoamps range. It's almost a near flat line on the negative x-axis. Okay, near flat line on the negative x-axis. And then breakdown occurs. And this is known as the Zener voltage VZ. There is a very small slope, or actually I should say there's a very steep slope. It's not a 90-degree angle line. There is a slight deviation, okay? So there is a small deviation from being an absolutely 90-degree vertical line. So in real life, there is a very steep slope of that characteristic. But for all intents and purposes, we treat it as a almost constant voltage at the output. So VZ, reverse bias, your V out will always be at a near constant level. And this is how we would analyze our Zener circuits, okay? It's always connected in reverse bias, and the output voltage is always equal to VZ. So V out will always be equal to VZ. And because it's in reverse bias, sometimes it gets confusing. If you refer to specifically just the diode current, diode voltage and diode currents are always measured with a positive reference at the anode. Okay, so VZ, even though we state it as plus 5 volts, if we are stating the voltage for the diode, it will be minus 5 volts because the reference, positive reference, is always at the anode. And the Zener current, of course, is just current flowing through it, but it's going from anode to cathode. We say it's negative, minus. And V out will equal VZ if V in is greater than VZ. The input voltage must be higher than the Zener voltage in order for the diode to hit the breakdown, VZ. If V in is right here, it's not going to turn on. Make sense? Right? The input voltage to the Zener diode must hit the reverse breakdown voltage, which is VZ. If V in is less than VZ, if V in is less than VZ, then the diode won't turn on, and V out will simply be equal to V in. That's it. Almost out of time. One final point is, so we had the rectified output. We gave it to a capacitor filter. Now we have a filtered output that has a small ripple. If the output of that capacitor is higher than a Zener diode that we are using, so let's say Zener diode of 5 volts, and we apply a filtered output of about 6 or 7 volts. If we feed that 7-volt filtered output into a Zener diode of 5 volts, the output would be a constant flat line at 5 volts. Okay, so we have a diode rectifier then a capacitor, and then a Zener diode. And the output of that Zener diode would be a flat line at 5 volts. And that's how you would obtain an actual DC output or DC voltage from an AC input. Okay, but that is a discussion for next class. We will analyze the Zener diode circuit using a load line as well as piecewise linear analysis, and then perform a analysis of a voltage regulation using Zener diode. I will see you all on Friday. Friday, I have a few things going on, so there are no office hours. I may perhaps be able to meet students for 10 minutes or so after class. And I'm also available at my normal hours for today and for tomorrow. But Friday, I have a seminar and I also have an off-campus appointment, so I won't be available. I already posted the announcement on Canvas. Okay. All right. Have a good day, and I will see you all on Friday.